Welcome to a lecture on bonding in materials for Bsc VI Sem students in 6.2 paper by Ms. A. Shirly Jones, Associate Professor and Head of the Department of Physics of V.B. Sanga's Virshada College, Ballari. In this chapter, Bonding in Materials, we are going to study covalent, ionic and metallic bonding with examples and discuss covalent, ionic and metallic solids and their properties. Now, what is bonding? We know that matter exists in three forms: solids, liquids, gases primarily, and now the understanding is there are five forms, that is solids, liquids, gases, plasma and liquid crystals. An atom is a basic constituent of all matter. Atom exists in groups to form molecules. Now, the process of bringing two atoms or more atoms together is called as bonding. Now, when two atoms come together, they approach certain minimum distance, or they can come attached to each other. Now, the distance between the centers of the two atoms involved to form a bond is known as bond length. Now, there are also forces which are involved when two atoms come together and they interact. Now, the arrangement of atoms in a solid material depends upon the strength, the character, the directionality of these bonding forces, which are cohesive in nature. Now, the bonding in a solid plays a very important role in determining physical, chemical and electrical properties of that material. Hence, an understanding of bonding in a material is important. Materials, in particular solids, their bonds involved in forming the solids are studied, tailored, fabricated so that they can be used for specific applications. Now, let us see what are the forces that exist between two atoms bonded. There can be force of attraction and force of repulsion. Now, the energy in a solid depends upon the sum of the individual energies of the atoms plus the interaction energy. When the atoms are in the ground state and are separated by a large distance, naturally the potential is zero, the energy is zero. But as the atom consists of moving electrical charges, that means electrons, one of the two things can happen when the two atoms approach each other. They either attract each other due to positive charge of the nucleus and the electrons in the second atom. Second, they repel each other due to the repulsive interaction between the electron cloud of the one and the second atom, or positive nucleus of the first and the nucleus of the second. The potential energy due to attraction is always negative, as atoms do the work during attraction. Now, the potential energy is the sum of the two energies and it is given by V is equal to V attraction plus V repulsion. Now, that can be written as alpha by r to the power of n plus beta to the divided by r to the power of m, where alpha and beta are constant of proportionality for the attraction and repulsion respectively. The forces between the atoms, which is negative, rate of change of potential with the distance is given by, you know that F is equal to minus dV by dx. So here F is equal to minus dV by dr, that can be equal to n alpha divided by r to the power of n plus 1 minus m beta divided by r to the power of m plus 1. Now, the variation of the potential with the distance and the corresponding attractive and repulsive forces are represented in the following graphs by dotted curve, and the resultant potential and force are represented by the solid curve. Now, you see the solid curve is the resultant potential. Now, in repulsive forces, it is different as shown in the graph. Now, we can understand few points from these graphs. At large separation V is equal to 0, F is equal to 0. As the atoms approach each other, they exert force on each other due to positive and negative charges in the atoms. When the atoms are separated by a few atomic distances, the repulsive forces between the light charges of the nuclei and the electron cloud slowly starts to increase. At some separation called equilibrium separation at 0, the forces of attraction just equals the forces of repulsion. Now, the potential energy corresponding to this separation reaches a minimum value. Now, we've seen that bonds have atoms which at bond length, having forces in between them, having energies. Now, depending on all this, there are primarily two kinds of bonds. The nature, the strength and the directionality of these bonds depend on the location and movement of the electron cloud involved. Basically, it is the electron or the electron cloud and its motion. Now, chemical bonds are of two types. One is primary bond, another one is secondary bond. In simple, primary bonds are between atoms and secondary bonds are in between molecules. Now, attractive forces in primary bonds are due to the valence electrons, which are high in energy state, to acquire 8 electrons in their outer shell by either sharing or losing the electrons, so that the atom will acquire a stable configuration. This results in the formation of primary bond with the net energy of the system reduced to a minimum. Now, few points can be noted here that every bond has an energy and the bond energy is expressed in kilojoules per mole. Otherwise, they also, or generally it is now expressed in electron volt per bond and kilocalories per bond. It is to be noted that 1 electron volt per bond is approximately equal to 100 kilojoules per mole. 1 kilocalorie is equal to 4.18 kilojoule. The energy per mole of bonds is not necessarily equal to the enthalpy of atomization. Now, this is a point just added. Primary bonds have energies in the range of 100 to 1000 kilojoules per mole. Covalent, metallic and ionic bonds belong to this group. Now, secondary bonds, which is due to the interaction of molecules, they have energy in the range of 1 to 50 kilojoules per mole. Van der Waals bonds and hydrogen bonds belong to this group. It is also to be noted that when a material is in solid state is formed, it is formed by the mixture of both primary and secondary bonds. In case of homonuclear atoms, the bond length is equal to the diameter of the atoms. In case of heteronuclear atoms, bond length is equal to the sum of the atomic radii of the two atoms involved in the bonding. Now let us understand the different kinds of bonding. I said earlier that there are ionic, covalent and metallic bonding. Now what is ionic bonding? Ionic bonding involves the exchange of electrons between atoms to complete shells either by adding or giving up electrons. Ionic bonds are non-directional. Now let's take the help of sodium chloride and try to understand this ionic bonding. The steps involved in the formation of ionic bond between sodium and chlorine can be represented as follows. Now sodium, the element, has atomic number 11 and its electronic configuration is 1s2, 2s2, 2p6 and 3s1. Being an alkali metal, the first ionization potential for sodium is relatively small and it's equal to 5.1 electron volt per atom. The outermost electron is removed by supply of this energy. That is, a sodium atom takes 5.1 electron volt, becomes sodium positive ion plus an electron. Now chlorine, which has got the atomic number 17, has got electronic configuration 1s2, 2s2, 2p6, 3s2, 3p5. As it has one electron short to have an octet configuration, it has high affinity to grab an electron. The electron released from sodium is now available so that chlorine takes up this electron. So that the vacant state in chlorine atom produce negatively charged ion. The electron affinity of chlorine is 3.8 electron volt per atom. So chlorine plus an electron gives a chlorine negative ion plus 3.8 electron volts. Combining sodium and chloride, we have Na plus Cl is equal to Na plus Cl minus 1.3 electron volt. That means 1.3 electron volt energy is formed. Due to this, there is a net increase in potential energy of 1.3 electron volt per atom. This is more than compensated by the decrease in energy due to electrostatic attraction between the two oppositely sodium and chloride charged ions. Now let us see covalent bonding. A covalent bond is also called as homopolar or electron pair bond, is formed by sharing of electrons by the two atoms so that the energy of the resulting molecule is minimum. Stable covalent bonds are formed between many non-metallic elements with half-filled outer electron shells. Let us now understand the formation of hydrogen molecule. Hydrogen atom has only one electron in K shell, and it needed one more electron to have its complete quota of 2 electrons in the first orbit. Two hydrogen atoms share their only one electron with each other so that hydrogen is formed. The two electrons equally belong to both hydrogen atoms so that both have their outer shell completely filled to have minimum energy as shown in the figure. Now let us understand the formation of chlorine molecule. In the case of chlorine atom, the outer electron shell of chlorine has 7 electrons, and hence each chlorine atom needs 1 electron to form the octet structure, that is 8, acquiring a stable structure. Octet configuration is acquired by both the chlorine atoms by sharing 1 electron from each other so that they belong equally to both the atoms, so that a stable molecule of chlorine is formed with minimum energy as shown in the figure. Similarly, the formation of oxygen molecule and nitrogen molecule is understood. Now, certain things are to be noted in covalent bonds, or the molecules which form the Covalent bonds. Covalent bonds are formed between homonuclear molecules such as hydrogen, oxygen, nitrogen. Covalent bonds are also formed between heteronuclear molecules such as HCl, methane, ethane, benzene, etc. Number of covalent bonds formed in between any two atoms is determined by the number of valence electrons, and it is given by a rule. Number of covalent bonds is equal to 8 minus the number of electrons present in the outer shell. In the case of covalent bonds formed in carbon and other elements, s orbital electron is excited to vacant p orbital, and these orbitals combine to form sp2 and sp3 hybrid orbitals. Now let us see metallic bonding. Metallic bonding is the principal force holding together the atoms of a metal. Now this type of bonding is the characteristic of element having small number of valence electrons which are held loosely so that they can be released easily to a common pool of electrons. Bonding results when each atom of the metal contributes its valence electrons to the formation of electron cloud, or it's also called as electron gas. The innermost core electrons tend to be concentrated in the vicinity of the nucleus of the atom, while the valence electrons have their most probable position near the surface to bond with other atoms. In the simplest model, metal ions are bound together in the solid metal by the interaction of the cloud of electrons that may be considered to move very freely. A schematic diagram of metal ions and their electron cloud is illustrated as in the figure. The electrons which are in the cloud belong to all the ions equally, and they move throughout the metal as free electrons. We can imagine metal ions in the crystal lattice or immersed in a pool of electron cloud. The most important characteristic of the metal bonding is the fact that every positive ion is equivalent. Thus, metal can show ductile behavior. This is due to the fact that under stress acting on the metal, the metallic atoms break at one location and the atom slips, and they again re-establish the bonds at some new location. It is to be noted that metallic bond arises due to the electrostatic force of attraction between the conduction electrons or the electron cloud and the positively charged metal ions. Metallic bonds may be regarded as sharing of valence electrons of all the atoms in a metal among lattice of positively stable, immobile, charged positive ions. And metallic bond accounts for many physical properties of metals such as strength, ductility, thermal and electrical resistivity and conductivity, opacity and luster. Now these are the important properties of metals which we can tailor. Now, let us understand the nature of the metallic bonding. The combination of two phenomena gives rise to metallic bonding. Well, what are they? Delocalizing of electrons and the availability of far large number of delocalized energy states than the number of delocalized electrons. The availability of a large number of vacant energy states results in conduction band. Now we know that in semiconductors we have got all the energy states empty in the conduction band so that electrons can come and sit in those energy states. Due to this, a free and random movement of electrons in the conduction band is possible. The free electron gas is held to positive ion core by metallic bond. The bond between the free electron and the positive nuclei. is the metallic bond. In an electric field, random movement of electron, gas or cloud is superimposed by the net movement of electron cloud towards positive potential, resulting in a net current in the material and conductivity of metals. When metal is heated, heat is transferred through vibrating ions in the lattice, that means positive ions, by quantum or acoustic energy known as phonon. Now, what is this phonon? Phonon is an imaginary particle designed or imagined or created which transfers energy in immobile positive ions sitting in lattice points. It is not primarily due to the electron movement as it is in the case of electrical conduction. So, electrical conductivity due to the movement of electron gas. Thermal conductivity is due to the transfer of phonon. Now let us come exclusively to the differences in these ionic, covalent and metallic bonds. Now the solids which are having these bonds are called as ionic solids, covalent solids, metallic solids. Now what are the basic differences? The first one are characteristics, let us say, and compare them. First is the nature of bond. Ionic bond is formed by the electrostatic attraction of oppositely charged ions, as we have seen in sodium and chlorine. Covalent bonds is formed by sharing of electrons between the atoms, as we see it in semiconductors. Now, metallic bonds are formed due to the attraction between positive ion lattice and delocalized electron gas. Now, the second thing what to be compared is their physical properties. Ionic crystals are transparent or colored by the characters absorption by ions. Covalent bonds are transparent, have high refractive index, and some are opaque, while metallic solids are opaque and reflecting. Now let's come to conductivity. Solids having ionic bonds are insulators. But they become conducting in solutions having ionizing solvents. Now covalent bonds exist in semiconductors except diamond, which is insoluble. Now metallic bonds or metallic solid, these are the electrical conductors soluble in acids to form salts. Now let us see how the melting point is differ in all these solids. Ionic solids have fairly high melting points. Covalent solids have very high melting points. However, metallic solids have moderately high melting points and they are good conductors of heat. Now let's come to the mechanical properties. In ionic solids, hardness increases with ionic charge, break by cleavage. In covalent solids, they are very hard. These break by cleavage. And metallic solids, they are tough and ductile except one element, that is tungsten. Now the examples of ionic solids are sodium chloride, calcite, magnesia, while covalent solids are diamond, silicon, carbon, rutile, and the metallic solids are copper, iron and sodium. Now the bonds, the types of bonds are studied and known their characteristics so that they can be tailored in order to create or fabricate materials for a specific use. Thank you.